anchoring midair images onto physical objects. Presenting is Hajime Kajima from the University of Tokyo, and I'll let him take the stage.
Thank you for the introduction. Today, I will talk about SkyAnchor, optical design for anchoring media images onto physical objects. We will have studying on the optical system of media images. In today's presentation, we focus on anchoring media images to physical objects. Anchoring means to attach media images to moving objects. The left one is previous method. Moving the physical object causes latency in the media imaging system, and the media images seems to follow the object with a delay. The right one is the proposed method. The proposed method does not cause any latency in principle and is effective for high-quality mixed reality applications. Here is the introduction of today's presentation. Mixed reality has been proposed to extend daily life objects with visual images. Media imaging is a promising way for glass-free mixed reality interactions. This movie shows the media imaging system named hover table. Previous work, such as hover table, can generate a static image of a specific location on the table. If the media image needs to be moved around the space, previous designs require position sensing and registration. Previous designs cause latency and the media image seems to follow the object with a delay. This is caused by delays due to the sensors, displays, and computational devices for position sensing, and occasionally actuators for moving the light source. Our approach is anchored imaging. This anchored imaging method generates moving media images anchored to physical objects without the need for position sensing and mechanical actuation. This is the contributions in our research. The first one is a new retroreflective system. This system consists of only optical devices. The second is zero latency anchoring of media images to physical objects. There are three aspects that need to be consistent across real and virtual world: illumination, geometry, and time. About consistency of illumination, previous work proposed a shadow projection of virtual characters to enhance depth perception of image position. To achieve consistency of geometry and time, previous approaches require high-speed tracking and actuation. It is a challenging problem to attach the image to a physical object strictly so that it moves with the object. In this paper, we propose another method to guarantee consistency of geometry and time between physical and virtual objects. This is a technical overview. The proposed system consists of three elements. The first one is a retroreflective system, which forms an object-anchored media image, I1. The second is an additive system, which forms a non-anchored media image, I2. The third is a light source attached to the rest of a physical object. As imaging device, we use an aerial imaging plate, AIP. AIP is easy to use and commercially available. AIP forms an image at the plane symmetric position. When you put a light source behind AIP, a media image is formed in front of AIP. This shows the detail of the retroreflective imaging method. AIP consists of two-layer micromirror array. The incident light from the light source is reflected by micromirrors. Then the media image is formed in front of AIP. In proposed design, we use AIP and two mirrors. Light from the light source L1 is reflected by mirror and forms I1 star. I1 star goes L1 star goes through the AIP and forms I1 star, and I1 star is reflected by mirror and finally forms the media image I1. The physical object is combined with the light source. When the user moves the physical object, the media image is anchored to the physical object. In the first prototype, the light source can come from the touch table on which physical objects are placed, using a mirror system that is attached at the base of the rest to reflect the light coming from underneath. To control what image is displayed on an object, we need to track its position on the table. The object is a daily life physical object, and the system can detect its position and rotation through the markers placed on the bottom of the rest. But there is still some latency. The latency in this prototype is due to the position sensing and the registration in the touch table. To achieve zero latency in superimposing, we propose a rest that incorporates a light source. The rest consists of the base of the rest, a mirror, and a smartphone. Light from the light source L1 is reflected by mirror in the rest and goes through the main optical system and finally forms I1. The relative position of L1 and I1 is always the same as long as the object is not lifted off the touch table. In addition, we placed a light source L2 that moves automatically using an actuator. This L2 acts as the light source for forming media image I2. I2 is not anchored to specific physical objects. Mirror is changed into a half-silvered mirror and I2 is added. By moving I2 with an actuator, the depth of I2 can be changed. A combination of the anchored and non-anchored setup enables showing media images whose position is controlled both by the user and by the system. As expected, the non-anchored part of the system suffers from delays due to the actuation. In this video, the fruit is a non-anchored image while it drops, but after it is put in the basket, it changes to be an anchored image. The visual range of this anchored image is a pyramid-shaped zone in front of the virtual AIP. Virtual AIP is the virtual image of the physical AIP by the mirror. The visual range is suitable for the moving mirror image anchored to the physical object. Although our calculations predicted a given visual range, we wanted to verify this experimentally. We also wanted to evaluate the quality of the mirror image, given that we use an inclined AIP that could reflect undesirable light, and our light source moves with regard to the AIP plane, and as such, the luminance of the generated mirror image may be affected. We measured the luminance at the center of the anchored image. The standard position of the luminance meter was decided to be the same as the center of the anchored image. We changed the height of the luminance meter to 3 points in order to take the motion of the viewer's head into consideration. The touch table was divided into 144 segments, and we placed the mirror type of the rest at all the points. This shows the luminance of the superimposed mirror image. The visual range was trapezoid form as was thought theoretically. In the lower viewpoint, when the image was closer to the viewer, the part of the image fell outside the visual range and was not shown. We also found that the luminance is higher at the center area of the display. This is because the luminance distribution of the display has such a feature. In the evaluation, we did not measure any undesirable image. We also verified that the mirror images was always exactly above the physical object, irrespective of their position on the table. This shows the anchored mirror images at multiple depths, regardless of the viewing point the image anchors onto physical objects. The current design of SkyAnchor has several limitations. First, due to the principle of real imaging, real images can be seen only behind physical object. This occlusion is a challenging problem. In addition, since 2D displays are used as a light source of imaging systems, the resulting mirror images are also 2D images. SkyAnchor has a limited interactive zone. When the user lifts the object from the table, the anchored image disappears. In addition, when the object is far from the main optical system, the anchored image has low resolution. The size of the image is another issue. The size of the anchored image is dependent on the size of the rest. In the implemented design, the height of the image is 100 millimeters. The size of the image can be enlarged by using a larger rest. However, a larger rest is more difficult to move. This is conclusion of our research. The first one is a new retroreflective system. This system consists of only optical devices, 2 mirrors, and an area imaging plate. The second is zero latency anchoring of media images to physical objects. The system reflects light from a light source anchored under the physical object itself and forms an image anchored around the object. Thank you for listening.
Okay, we have time for several questions. Are there any questions? So I can start off while you guys think of a question. I'm wondering if there's a lot of setup required to calibrate the position of the midair image onto the physical object, or is it a straight one-to-one mapping? Is there a lot of calibration required to get the position of the virtual image in the right position relative to the physical object, or is it a direct mapping?
This research cannot detect, don't need the calibration or registration. This research, the merit of this research is don't need the calibration and registration.
Thank you. Are there any other questions? If there are no more questions, then let's thank the speaker.